Swayam Prabha. Digital India. Educated India.
Having discussed some of the very basics concepts of electrical conduction in solids, followed by the introduction of the band model and differentiating between metals, semiconductors and insulators, let us try to look at actual ceramic materials, how they behave in terms of the band structure as well as the charge transport phenomena in real ceramic materials. Here is a list of electrical conductivities of a few selected oxide ceramics. You will see there is a very wide spectrum of electrical properties, starting from the insulators over here, then you have semiconductors. There are some metals, some ceramics where there is a metal insulator transition, and then you have some metallic behavior in them. So, different kind of electrical properties are available in the host of ceramic materials, some of which we have discussed briefly earlier. For example, sintered aluminum oxide, it is a highly insulating material. So, also the complex compounds like steatite porcelain, magnesium silicate, which is very extensively used in industry as an insulator. Then of course, the high voltage, so called high voltage porcelain which used in transmission lines, all of them are highly insulating materials, and there are some data you can see at 500 K and 1000 K, and you will find the insulation property or the conductivity increases as we increase the temperature. That is the normal behavior of an insulator as well as the semiconductors here. Only difference is the conductivity of semiconductors are at a slightly higher level than the insulators. So, these are the transition metal oxides, and because of their particular defect structure and the concentration of point defects and resulting non-stoichiometry, we do get semiconducting behavior in the oxides. Then there are some relatively uncommon oxides like VO, VO2 and etc. You will find the conductivity, there is a huge gap or huge change of conductivity from a low temperature to a high temperature. Okay. So, sudden jumps, unfortunately the curves are not here, but once you refer to curves you will find there is a 8 orders of magnitude change from 100 K to 500 K. So, which means there is basically a transition is happening from an insulator to almost like a conductor. Same is the case with here. You will also find a huge change between 100 degree and 500 degrees, and there is a sudden sharp change in the conduction mechanism, and also there is a phase transition. Compared to all of them, here is a material rhenium oxide Re2O3, we will find if you look at the values here, you will find the conductivity actually decreases, conductivity slightly decreases when the temperature is increased. So, it is basically a metallic behavior kind of situation. So, among all the different kind of ceramic oxides, we find different properties, and obviously they are related to their structure, their defect structure, and also the basic conduction mechanism which is valid for them. Well, this particular diagram we have discussed briefly in an earlier class. We have seen the origin of band model or the conduction or the band gap, the valency band and the conduction band, how it comes across or how it comes up with the introduction of the variable potential of the electrons in the solid. Here is a different approach. We can visualize the band gap from a slightly different angle. Here these are the orbitals, these are the orbitals of different atoms which are normally there, and these are the inner orbitals or inner levels, and this is the outermost orbital. Now, outermost orbital the diameter is larger, whereas these are smaller. So, if you are bringing two different individual atoms, isolated atoms from a distance, then the outermost electron will come or interact with each other of the two different atoms first, and then the others will interact. Okay. So, normally there will be a equilibrium distance of separation depending on the particular structure of the element and the crystal structure in which it crystallizes. So, there will be always interatomic spacing, and that also determines the lattice parameter and so on. Here initially when the distance of separation is much larger than the interatomic spacing or the equilibrium interatomic distance of separation, there is no interaction between the orbitals of the two atoms. So, they have a discrete energy levels, a single energy levels, whereas when they come closer to each other, they interact, they overlap, the electron cloud overlap with each other, particularly for the first outer orbitals, and then there is a degeneration, the energy gets splitted and you have a band of energy here. Both wherever there is a overlap, there will be a band of energy. The first, this gets splitted up and degenerated the highest level, that forms the highest level, whereas the next one is this next inner level, and that also gets splitted up, and you have a band of energy here, whereas the inner cores, the inner levels do not interact, still at the interatomic spacing or the equilibrium distance of separation, there is still not interaction between them. So, they remain unchanged. So, they are actually discrete levels, inner levels remains as discrete levels, whereas the outer levels gets degenerated into bands. So, there is quasi continuous bands or quasi continuous energy levels available at the outer orbitals, whereas they do not have, they have a discrete energy, they remains unchanged. So, these two last, the highest bands can be often considered as the valency band and the conduction band, whereas the gap between them is called the band gap. So, this is also another approach which we can take while considering or while visualizing the band energy of a system. This becomes quite useful, particularly when we are talking about ionic solids like the ceramics and the oxides. So, with this background, let us try to look at what happens in the band diagram, because band diagram is one of the basic concepts to understand the various different charge transport phenomena or electrical conduction or resistance in a material. So, we look at how exactly we arrive at the different band diagrams in a particular oxide in particular. The oxides are predominantly ionic in character, their bond, the chemical bond is ionic in character mostly. Unlike in metals and elemental semiconductors, the electrons in an oxide lattice are relatively tightly bound to the specific ions because of the strong interaction, because you have an ion core and they are strongly positive and the electrons are strongly negative, or there will be cations and anions. So, the electrons which is negatively charged obviously, they have a much stronger bond with the positive ions, and therefore, their situations are slightly different compared to what we get in metals or in semiconductor. In metals, it is a electron cloud and they are completely unlocalized or delocalized, whereas semiconductors is little more localized, and in oxides it is much more localized, so that they are actually much tightly bound to the ion core. So, there are difference. So, the band, the nature of the band is certainly different, and we will also designate these bands in a different way. So, that is what we like to look at. The energy levels of an electron in an oxide structure is therefore conveniently designated by the particular ion to which the electron is associated with under different situations. So, the electrons or the bands are actually designated as the bands associated with the particular cation or the anion. Okay. We will look into it what exactly it means. So, the energy levels are designated by that particular cation or the anion when the electron is associated with that particular ion. In an oxide lattice, the inner electrons of an oxygen ion occupy discrete energy levels, whereas the outer electrons, by interacting with the outer electrons of the neighboring ions, give rise to degenerated energy bands, just we have discussed earlier. So, degeneration takes place when there is overlapping of the electron cloud of the two atoms or the ions in this case. The energy of the highest occupied band associated with the oxygen ion corresponds to the ionization energy of the oxygen ion. Of course, we are first considering the situation what happens in the oxygen ions. We can also consider very similar things for the cations or the metal ions. So, this is what happens. The energy of the highest occupied band associated with the oxygen ion corresponds to the ionization energy of O minus ion, that is the conversion of O minus to O2 minus ion. So, the overall energy change is here. We are considering O minus ion, that is not O2 minus to start with. When you add this electron, it becomes O2 minus. So, we are looking at what is the energy change, what is the change of energy with this. Okay. So, in fact, it will be from the free space, as if we are adding an electron from the outside to the oxygen minus ion in the lattice, and as a result we are getting O2 minus in the lattice, and we will look into what is the energy change. So, the energy required for this reaction may contain three different terms as follows. Okay. First is the electron affinity of the O2 minus ion, that is designated as EA. The electron affinity, what is the energy change by that process of adding one electron to the O minus ion. Then it becomes, it can write O minus free space and also O E minus in the free space. That means, a singular oxygen ion is there and a singular electron is there. When we are adding together, what is the energy change EA, and both of them, and finally O2 minus, which is also in the free space. It is not hindered by any other interaction of the surroundings. So, the electrostatic energy, that is the second term, the EM, gained by adding an electron into the positive potential region of the lattice. That means, free space is coming to the vacant lattice site, okay, E minus, that is another energy term, that is another energy term which is EM. Okay. So, this is the first energy term, this is the second energy term, and the energy of the lattice polarization EP arising from the electronic addition to the lattice. So, when electron is added to the system, then it surrounds a electrical field, it generates an electrical field, and that electrical field interacts with the other surrounding ions, and the lattice gets polarized. The lattice gets polarized, and so some readjustments takes place, and that also requires certain energy. So, there are 3 different energy terms: EA, the electron affinity, then it is the energy gained by the system because of the negative ion is being added to the system, positive potential of the lattice, okay. And then there is a polarization because of the addition of a charge to the crystal lattice. So, the total energy change, in summary, the energy of the electron in the lattice band, or the band energy ultimately, with respect to that in the free space, is summation of the 3 components indicated above. Okay. So, it is E minus equal to, I mean E O minus, sorry, E O minus equal to E A, which is the terms explained earlier. This is a negative term because the energy is gained by this process, by this particular process. This is a gain in energy, this one, and then EP is the polarization energy. The convention is to level the band when the same is occupied. That means, thus E O minus is approximate energy level of the O2 minus band. Okay. The convention is, we do not designate this is O minus, although we are talking about what happens to O minus, we are adding an electron. That means, a O minus ion is changing over to O2 minus by accepting one electron from the outside. By that process, whatever change is there, that is the change, or that is the energy level of O2 minus band. O2 minus band. Similarly, one can also visualize the band energy of the cation. Okay. So, we have just discussed the how we can designate the energy level of an electron associated with O minus or O2 minus. Basically, the band will be designated as O2 minus. It will be clear in a minute when we discuss show the picture. Now, in the case of the cation, the energy for the cation level is given by similar terms M3 plus. Now, it is electron is getting added to a cation. So, we start with as if we have a 3 plus ion, M3 plus ion. When the electron is added to the system from the free space, from outside the lattice, then we are actually, it is changing over to 2 plus. So, the band ultimately will be designated as M2 plus. So, the M2 plus, the band of the M2 plus is I3. This is I3 is the ionization potential, third ionization potential of the metal M. In case of negative ions, it is primarily the electron affinity, and positive ion is the ionization potential. It is the same thing. So, EM appears as a positive term here, as the electron is being added to a positively charged location of the crystal. Okay. So, this is becomes this EM, which was earlier negative term, is now a positive term. These two remains as the positive term. So, ultimately the total summation is EI3, the third ionization potential energy of M3 plus if it happens, and then EM, here is also the EM component, that is the energy gained by the electron into the positive goal. That is what we earlier discussed here, and here also the EM is there, but it is a positive term. Earlier it was negative term, it was a positive term now, and this is EP, polarization is always positive. So, for transition metals, of course, that is a general thing for non-transition metal oxides. For the transition metal ions, the energy expression will contain an additional term arising from the fact that in presence of the oxygen ions, certain d orbitals are preferentially stabilized than the others. So, there is slight adjustment, in the energy term, particularly when the transition metal ions are there. So, there will be fourth term which has not been designated here, there will be a small change, and that will be a fourth term particularly for the transition metals. Thus, the final energy band diagrams of one transition metal NiO and the non-transition metal MgO are given in the next slide. So, in reference to that particular diagram, it will be more clear. This is what it looks like, and these are the different steps. These are the different steps. 3 steps we have discussed, particularly for the non-transition metal oxides, and a transition metal oxide like NiO. A 4th step I mentioned is because of the preferential stabilization of some of the D cells, there will be slight change in energy. So, what by step how the energy levels are changing, energy level associated with this cation, both the cations and the anions, the energy of the electron associated with the cations or the anions. So, the energy diagram here represent 2 representative metals, one transition metal NiO and a non-transition metal MgO. Different steps A, B, C, D represents different components of the energies as explained in previous slides. So, what we have talked about, that is what is given here, but this is the energy scale. We started with, let us say for transition metal or let us say for the non-transition metal to start with, we have MgO. So, we have bands like this Mg2 plus, Mg plus, O2 minus. These are the 3 levels of the these are in isolated ions, isolated elements. Okay. So, if you take the isolated elements, it becomes like that, and then or sorry, not the isolated element, it is for the first step, that means the electron affinity and ionization potential. Okay. If you just look at the electron affinity and ionization potential of these ions, the relative energy levels are like this: Mg2 plus the lowest energy, Mg plus the next highest energy, and O2 minus is the highest energy. Yes, incidentally, this is the more or less the situation in other oxides also, non-transition metal oxide also to start with. Okay. To start with, Ni2 plus as the lowest, Ni plus as the next lowest or next highest, and then O2 minus as the highest energy level, so far as the electron affinity and ionization potentials are concerned. Then we have added the electron. As soon as we add the electron here, the in fact the energy goes down from there to there, and this goes up. Okay. So, the energy levels goes up here, whereas the oxygen goes down. So, the cation energy goes down, goes up, the energy level of the electron added to the cation. Okay. Then there is a polarization. Because of the polarization, all these energies, again the Mg plus will go down, whereas oxygen will go up and Mg2 plus will also go up. Okay. So, these are the different components of the energy level, energy associated with the different steps involved, and finally, you will see that Mg plus is the highest, O2 minus is in between, and Mg2 plus is the lowest. So, this is the lowest energy, this is the next lowest or intermediate energy, and this is your highest level of energy. This is in comparison to here in a transition metal is more or less same, but slightly different. Okay. This comes down much below Ni2 plus. Okay. Here oxygen does not come below Mg2 plus. So, the oxygen is in between, whereas here oxygen comes much below the 2 cations or the 2 state of the cations, Ni2 plus and Ni plus. Okay. So, these are the conduction. Of course, as I mentioned, there is an additional term, the 4th step, and but the change of energy is very insignificant. Okay. Whereas, this 4th step is not there in MgO, the insulating oxides. or non-transition metal oxides. So, you will get finally these are the energy levels of, as I said, they are designated according to the status or the charge levels of the cations or the anions when the electrons have been put in there. So, in this case, in the transition metal oxides, the highest level is Ni plus, the next lowest level is Ni2 plus, and oxygen is much below. In case of non-transition metal oxides, the highest level is Mg2 plus, not the Mg plus as in case of nickel, but the next lower level is not the cation, the oxygen comes in. So, this becomes your valency band and this becomes the conduction band here, whereas here it is between nickel 2 plus and nickel plus. So, it is between the two cations, that is the valency band and the conduction band. That is an important difference between transition metal oxides and the non-transition metal oxides or insulating oxides and semiconducting oxides here. With this, we go to the, now we are talking about the band diagram of an oxide as per the earlier designation. So, the band diagram of a typical insulating oxide, this is an insulating oxide including the energy levels of all possible point defects. Now, in this is for example, we have seen an insulating oxide here. So, the O2 minus here and Mg plus. So, this is actually O2 minus, it can be O2 minus, it had been written in a different way of course here that is M at the M site with a negative sign, okay, with a negative sign. It need not be written like that, one can also written differently, but what is more important here is what I am trying to show is these two levels. These two levels are basically the valency band and the conduction band. And the other important issue I want to mention is the position of some of the defects. So, the defects also has some energy levels. We have earlier discussed about the point defects of different types, metal vacancy, oxygen vacancy, they are charged or neutral vacancies and metal interstitials as well as oxygen interstitials. So, these different varieties or different types of point defects also have energy levels, that means electron associated with that have the energy levels which falls within the band gap, the main band gap of that particular oxide. So, this is the two bands, the valency band and the conduction band, and the once again this is an MX kind of oxide. So, you have metal interstitials, a neutral X here denotes the neutral, that means it is not a charge defect, it is a neutral defect. Similarly, oxygen vacancy is a neutral defect, these are not negative signs, these are actually the levels level indicators. So, this is the level compared to that or compared to this energy, and so these are not negative signs. Here you have metal vacancy with a positive charge, one positive charge, and metal vacancy with double positive charge, sorry, these are negative charges, effectively negative charges, because the positive charge is missing. So, it is effectively a negative charge. Now, these are the two, in each case there are pairs, is Mi x, Mi dot, Vo x, Vo dot. Here it is Vm single dash or single prime, single prime and as well as double prime. Here is OI prime and OI double prime. Okay. Now, these are actually the state of ionization. Okay. This is singly charged and this is doubly charged, because M has basically two charges, M2 plus, this is M2 plus, O2 minus. So, here both the charges are not there. So, it is singly charged, whereas next level it is goes to the doubly charged. Now, these are more prominent or more predominant defects, the doubly charged ones, this one or this one or this one and this one. Now, there is a difference also have to be noticed. Here it is doubly charged, but this has not been shown as doubly charged or positively charged, only single dot has been kept. This is single dot and this is single dot, whereas this is neutral and this is neutral. On the lower side you have both single charge and double charge, single charge as well as double charge. On the top it is actually single charge, neutral and single charge, neutral and single charge. That is because the way we have designed it, designated it. Okay. When the electron is there, actually it is a single charge. It was originally a single charge. Since it has been occupied by an electron, so single charge has gone to a neutral, and that is the designation, that is as per designation, because we have made a statement earlier that the energy levels are designated when the electrons are occupying that energy level. So, that is the reason a single charge has been designated here as a neutral, because it was single positively charged. One electron goes there, it becomes neutral. This is also single positive charge, when electron comes here it becomes neutral. Here the neutral, to the neutral one electron has been added or not added, actually it is removed. Okay. So, it becomes a positive charge, effectively positive charge, right. So, this is one kind of designation. The other thing is, this is our valency band, and the energy levels closer to that actually is the acceptor levels, because they will accept electron from here and create holes in this valency band. So, they will accept electron. If they accept one electron from here, it will change to this. If they accept two electrons, they will change to this. Similarly, the same case with this. This will accept one electron, it becomes negatively charged, one negatively charged, they have two electrons, it will negatively charged like this. Now, here it will donate electrons. A neutral atom has already it will donate electron and becomes a neutral, and this a positively charged interstitial will donate electron and becomes neutral, and then one more electron when will be donated, it will be actually negatively charged, singly positive charged. Okay. So, both Mi and vacancy which can donate electrons are actually act as a donor levels, whereas the Vm or the vacancy and the oxygen interstitials which can accept electron will act as acceptor levels. So, compared to other semiconductors, here it is a little different in the sense the defects itself. Okay, we do not have to add any impurity to create acceptor or donor levels. The defects, point defect themselves act as acceptor or donor levels within the oxide. Okay. So, they have their energy levels and they are within the band gaps. So, they actually create states, energy states which can act as donor or acceptor levels. So, this is a very important difference from the normal semiconductor when we talk about the oxides with that. So, without adding any impurity, you can have a p type conduction and an n type conduction, which we have discussed earlier, okay, which we have discussed earlier when you are discussing about the defect formation as a function of partial pressure of oxygen, some of them do act as a acceptors or a p type conductor, but some of them others act as n type conductors. This is a very specific example of a MgO, and this is the valency band of MgO, and this is the conduction band of MgO, and this is the 3s0. That means the electron has been is not there, okay, but once we add the electrons, it becomes 3s2. Here it is already electrons are there. Okay. So, the valency band of 2p6 or Mg2p6 actually acts as the valency band, the next highest level, and this is Mg 3s0 is become the conduction band. Okay. Now, the total band gap is of the order of about 8 electron volt, and as per definition this is an insulator. However, if some point defects are created, for example, Mg a vacancy, singly charged magnesium vacancy or a doubly charged magnesium vacancy will act as an acceptor. Okay, they will accept, and the typical energy levels are about 0.5 electron volt in this case and about 1.5 electron volt in this case. So, this is singly charged and this is doubly charged. We mostly get doubly charged ions. So, it gets a energy states within the band, and therefore, conduction is possible. To some extent conduction is possible. Okay. Here it is oxygen vacancy, that means intrinsic vacancy, this is magnesium vacancy and this is oxygen vacancy. Once again it is about 0.5 electron volt here, and this is doubly charged, sorry it has not been mentioned here. This is next ionization of this level. Okay. So, this is about 2 electron volts from the top. Here is another type of defect, which is aluminum has been added as an impurity to the magnesium site, and this is the aluminum at magnesium site with a neutral charge, and that is about 0.5 electron volts. So, this is a typical band diagram of a insulating material like MgO, and then by adding or creating vacancies, creating some defects, either metal vacancy or oxygen vacancy, you actually add certain states, energy states within the band gap, and one can increase the conductivity of them. So, aluminum, by adding aluminum you are actually creating a state, and so the electron transfer can take place there. This we have already discussed earlier. Once again I will try to look at it in a slightly different context. Once again all ceramics, the charge carrier density is strongly dependent on the partial pressure of oxygen with which it is getting equilibrated, and looking at it as I mentioned earlier when we were trying to discuss the defect concentration, this diagram was considered earlier in association with the defect concentration, but here we are talking about the conductivity, and there is a strong correlation between the defect concentration and the conductivity here, whether it is ionic conductor or an electronic conductor. For the time being we are basically looking at this part of the diagram or this part of the diagram. Here you will see the highest conductivity or the highest concentration is actually N or the electron concentration. So, this is the relationship neutrality condition here, and this is the neutrality condition there. So, it is oxygen because it is a very high oxygen rich side. So, oxygen interstitials are possible, and corresponding you have positive holes. So, that is the neutrality condition here, where on the lower side you have oxygen vacancy, and therefore, you have negative electrons or N type conductivity. The highest defect concentration is this. Okay. So, it is p type on this side, this is stoichiometric crystal. So, it is n equal to p, that is intrinsic semiconductor, and then it is a n type semiconductor on the lower PO2 side. Here also we find defect concentrations are like this, it is n on the lower PO2 side, and here p on the higher PO2 side. The only difference here is this value, this electronic concentration or electronic compensation or the equilibrium constant for n and p is lower than the oxygen vacancy, oxygen interstitials. So, this value is higher, the plateau here is because of this neutrality condition, that is oxygen vacancy and oxygen interstitials. That means, in this region it is the ionic defect concentration or the ionic compensation is predominant over the electronic compensation. So, the concentration of oxygen vacancy and oxygen interstitials are much larger than the concentration of the electrons or holes. In this diagram, it may corresponds to another oxide. This diagram may be valid for one kind of oxide, and this may be valid for another group of oxides. So, the difference here between this and that, as I mentioned here, this is in the stoichiometric crystal, it is the ionic compensation which is important. So, the neutrality condition is oxygen vacancy to oxygen interstitial. Here neutrality condition is electron is to hole, or the concentration of the electron is equal to the concentration of holes. So, this is an electronically conducting material, particularly in the stoichiometric crystal range, and here it will be an ionically conducting material. So, a ionic conductor will have a diagram like this, whereas a electronic or semiconducting oxide will have a diagram like this. This will be a stoichiometric, a non-stoichiometric compound basically, or non-stoichiometric oxide, whereas this will be stoichiometric or mostly stoichiometric oxides until unless they are equilibrated with very low PO2 or very high PO2, right. So, those may be attained, may not be attained, but it all depends which particular region the material has been equilibrated, and with respect to this diagram the atmospheric pressure where exactly it lies. Okay. The atmospheric pressure for some oxides may be here, for some other oxide it may be there, atmospheric oxygen partial pressure. So, depending on that, either one oxide will be permanently or predominantly a ionic conductor or predominantly an electronic conductor. So, this is the importance of this diagram, and on this diagram we have to place the atmospheric condition with respect to that particular oxide. So, these diagrams have been of course drawn only for a constant temperature. We are not considering the temperature effect here, it is the only partial pressure dependence at a particular temperature. Now, in that context, these have been discussed earlier also, but I will just give you some examples. For example, Cu2 minus XO, that means a cation vacancy, and because of the monovalent, this is copper here is a monovalent, and therefore, the because it is a cation vacancy, it will be a p type conductor. Okay. And if you plot log PO2 to log conductivity, you have a positive slope of, in this case it is 1/8 positive slope, and the band diagram now will look like this, as we have discussed in case of the MgO here, or generalized band diagram. Here the vacancies, the metal vacancies will have a acceptor like characteristics, and these will be the neutral vacancy, and this is the single vacancy or singly charged vacancy. So, this energy will be low, this energy will be high. So, if you have a singly charged vacancy, it will give rise to a conductivity like this, and it will act as a p type, and therefore, it is a acceptor. So, electron will transfer from this valency band to this acceptor level, and you will get a hole there. So, that is a typical situation of Cu2 O minus X, Cu2 2 minus XO, and this is another example of a semiconducting oxides, once again created because of the non-stoichiometry, and this non-stoichiometry here is because of metal interstitial, and metal interstitial act as a donor, and therefore, it is a n type semiconductor with a negative slope with PO2 log conductivity log PO2 with a negative slope, and the energy levels will be like this. Okay. Now, in this case zinc is divalent. So, there are 3 energy levels possible. One is the neutral level, and there is the singly charged level, and there is the doubly charged level. So, E1, E2, E3, E3 will be higher than E2 than E1, and they will act as a donor levels. Okay. These point defects will act as a donor levels, and they will act as a, and the overall conductivity will be a n type conductor. Now, we have seen this diagram earlier. Okay. This is just a modification of that, and this was that diagram was shown, the generalized diagram, which was shown in terms of the log concentration. Okay. We are not talking about the conductivity there, we are talking about the concentration. Of course, the concentration is very much related to the conductivity, and that is why this has been plotted as conductivity, and nothing, it is as we have seen, conductivity is just any mu. So, the n is the number of concentration of the charge carriers. So, the here the highest level or the higher concentration is of the n type, and on this side is p type. Okay. And so, the dotted line is actually the conductivity, and the final conductivity. So, the whole the material throughout the PO2 range will act as a semiconductor, because the highest concentration level is because of either for the electrons or the holes. However, they change their character at some intermediate PO2. Okay. There is no unlike the earlier diagram, you have a flat portion here where n is equal to p, that means it is a intrinsic semiconductor. In this PO2 range, it is an intrinsic semiconductor, and then it becomes a kind of extrinsic semiconductor because of the vacancy creation or because of the interstitial creation or vacancy creation on this side. So, in this diagram, that particular portion is missing, there is no intrinsic, that means either it has a negative and then positive, there is no intrinsic region. These concentrations are not immaterial to us, although there are some plots have been made in, and that means calculations can be done, but in reality this is the concentration which dominates, and therefore, that will whatever conductivity we will get, it is because of these highest concentrations and not the lower concentrations. So, that also need to be remembered. So, the conductivity arising from the oxygen vacancy in the same material will be like this, there is a constant region there, okay. But these are immaterial to us, because that will not get reflected in the ultimate measurement or ultimate property. So, what will reflect in the ultimate property is the highest concentration, whatever is the highest concentration in this region, that is the electron concentration on the lower side, lower PO2 side, and hole concentration on the higher PO2 side, they will dominate the conducting behavior or conducting properties. These are only for sake of our understanding. Well, having discussed all this, let us have a different kind of semiconductor. It is called valency controlled semiconductors. So far we have discussed kind of intrinsic behavior under different partial pressure range, how the defect concentration changes and how the temperature effect is also there. But we have not discussed so far what is the impurity effect. Just like in elemental semiconductor, germanium and silicon, if you add some donut doping, or accepted doping, you do get enhanced conductivity as well as a changeover from intrinsic conductor to the either p type or n type, depending on the type of the impurity you add. In this case also, in oxides also, one can add certain impurities, add certain other oxides and make the conductivity constant. It can be independent of PO2, it can be independent even with temperature, and this is what we call the valency controlled semiconductor. That means basically the valency of the host cation changes, which we have seen earlier, because that also changes because of the creation of defects, the intrinsic defects, but here we are inducing some defects, inducing some changeover of the valency of the cation, and that is how it is called valency controlled. The valency is controlled by adding certain impurities. An example here is Ni 1 minus XO or NiO basically, which is a p type conductor, and because of cation vacancy. So, we have a cation vacancy there. So, it is a p type conductor, and an intrinsic situation, if we do not add any impurity to this, this is the kind of defect reaction, half O2G, it is O at O side, vacancy of the nickel with a double prime, considering a doubly charged situation, not a singly charged situation. Normally, although for our discussion we have discussed in earlier slides that singly charged defects are also possible, but they are not so favorable. Primarily the doubly charged things, doubly charged defects are normally considered as the favored defects. So, we will have two holes, positively charged holes. Now, in that we have added Li2O. Li2O is a lithium oxide with lithium having monovalent or a single positive charge compared to Ni double positive charges, and that is why by adding about x by 2 amount of moles of Li2O to 1 minus x NiO and then some adding some oxygen, this is the kind of compound, or this is the kind of solid solution we will get, because lithium goes into solid solution with nickel oxide, or it replaces nickel in the nickel oxide's lattice. So, that is why we are adding about x amount of lithium plus 1 plus and removing 1 minus 2x or 2x amount of lithium nickel, and then these are 2 plus. By adding x amount of lithium, x amount of nickel is converted to 2 plus to 3 plus. That is what we call, we are controlling the valency from outside by adding certain allovalent impurities like lithium. So, Li2O goes into nickel, creates 2 Li Ni with a single prime, because Li is one less positive charge. So, it is effectively a negative charge, and in the process creates 2 holes. These 2 holes are actually written here as 2 Ni3 plus. So, effectively these two holes are situated or getting attached to the nickel site or the nickel 2 plus site and converting it to nickel 3 plus. So, it is because of this 2 plus and presence of 2 plus and 3 plus, we have a conductivity, we are inducing conductivity by adding nickel, and the concentration of the holes P is proportional to Li, the concentration of Li. It is not dependent or not controlled either by PO2 or by temperature. So, it becomes more or less temperature independent, except of course, there will be mobility term will change, but the concentration of the nickel of the holes, the concentration of the charge carrier here will remain fixed by the concentration of nickel. So, in any particular sample, if we prepare with some percentages of nickel, the conductivity of nickel oxide will remain constant. It will be independent of PO2. Another example is similar example is Fe2O 3 minus X. It is an N type conductor, and this is the intrinsic defect reaction. Here it is TiO2 gone to Fe2O3, and since it is a 3 plus is getting replaced by 4 plus, 3 plus is getting replaced by 4 plus. So, we have a effective positive charge and corresponding electrons are generated. Earlier it was sorry, there is a mistake over there. This is not nickel, it should be Fe. Right. So, Fe 3 plus, which was Fe 3 plus originally, has gone to Fe 2 plus by adding one electron. So, this concentration of electron is actually proportional to the number of titanium added or titanium atoms added. So, once again, earlier example was a P type conductor controlled by the addition of impurities. Here an N type conductor is controlled by the addition of another impurity of a different valency. So, earlier it was a lower valency added to the higher valency, here it is a higher valency added to the lower valency. So, that is the reason why it is getting the type of conductivity is also different. And these are the conductivity curves or resistivity curves here as a function of lithium content for the NiO and as a function of Ti content for the Fe2O3, and there is a sharp fall in resistivity when you add more and more number of lithium ions or more number of titanium ions to Fe2O3. So, both of them as a you can control the resistivity or increase the conductivity by this kind of valency control mechanism or of the oxides particularly, and these conductivities are independent of PO2 and mostly independent of temperature, because temperature of course will have some effect. So, far as the mobility is concerned, the concentration remains constant, but the mobility may get changed, and therefore, there will be some change in conductivity as a result of temperature, but PO2 it will be completely independent of PO2. Well, the time is up. So, we will close our discussion for the time being. We will continue this in the next class. Thank you very much. Thank you for your attention.